Hello, my name is Richard Wiswell. I am currently a Master's of Science student in the Electrical and Computer Engineering Department at the University of New Hampshire. Today, I will be discussing the impact of dynamic power factor correction on the grid. Total supplied power is made up of both real and reactive power. The real power does the work. Reactive power is required to maintain the voltage required to move the active power through the lines. If the load exceeds the ability of the voltage to support it, the voltage drops and the current increases. This increase in current leads to the overheating of equipment and overloading of lines. Reactive power is needed to prevent this voltage drop. Declining voltage reduces the reactive power available from capacitor and line charging, leading to further voltage drops and eventual voltage collapse. So, what causes voltage instability? Voltage instability can be caused by a disturbance, an increase in load, or a change in a system's conditions. In addition, harmonics and transients generated by the fluctuating loads and some VAR compensators also destabilize voltages and adversely affect power quality. A network unable to generate sufficient reactive power to compensate for changes may be susceptible to plummeting voltages and the collapse of the system. Therefore, the ability to analyze and maintain voltage stability is crucial to maintaining a reliable and efficient electrical grid. Since more current flows through the lines than is needed, the extra power dissipates as heat when reactive current flows through wires, switches, and transformers. Power factor is the percentage of supplied power that is usable for work. Reactive power reduces the power factor and increases power consumption. The problem becomes how to balance the use of reactive power to stabilize voltages while reducing the overall power consumption. The goal of this research is to optimize reactive power levels to maintain voltage stability amid fluctuations in load, while increasing efficiency and reducing power consumption. This will be accomplished by means of dynamic power factor correction. The hypothesis for this project is that a model can be developed to determine the optimum level of reactive power for any given segment of the grid. I plan to test my hypothesis by simulating the flow of power through a variety of existing flexible alternative current transmission systems, or FACS devices. I plan to develop a model to determine the optimum reactive power through any given transmission line segment under any given load. The model will be developed by running a series of computer simulations of the grid using a static VAR compensator, or SVC, a static compensator, STATCOM, a thyristor-controlled series capacitor, or TCSC, and a static synchronous series compensator, or SSSC, first individually, then in combinations, to determine which devices and configurations produce the highest power factors consistent with maintaining adequate reactive power for voltage stability over a realistic range of loads. These currently available FACS devices each have their benefits and drawbacks. I hope to find that the incorporation of several different FACS devices in one model will compensate for the drawbacks of just a single device. As electrical power demand has increased over the years, power companies have needed to improve both the efficiency and the reliability of the grid to compensate for the ever-increasing and fluctuating loads. Various means of power factor correction have been used to accomplish this task. Back in 1914, fixed shunt capacitors were used to compensate for the lagging current draw, providing static compensation. Later, switched capacitors, synchronous condensers, and saturated reactors were used to achieve dynamic compensation. The development of the thyristor made fast reactive compensation a reality. The static var compensator, or SVC, which was developed in the early 1970s, paired thyristor-controlled reactors, TCR, in parallel with 4 fixed harmonic filters to generate sufficient reactive power while reducing harmonics. The SVC reduces lagging reactive loads, eliminates harmonics, and provides a stable power supply. Changing the firing angle to the thyristor changes the current through the reactor, making the SVC a dynamic system. The development of devices capable of dynamic power factor correction allowed the system to compensate rapidly for fluctuations in load. The static compensator, or STATCOM for short, is a solid-state shunt-type device that generates reactive power using self-commutated power electronics instead of capacitors, inductors, and thyristors. It can generate and absorb reactive power about equally and control voltage efficiently. This in turn reduces the risk of voltage collapse. The thyristor-controlled series capacitor, or TCSC for short, uses a series capacitor in parallel with a TCR to control the flow of power by modifying the reactance of the line, which is a function of the firing angle of the TCR. It uses the series impedance on the line to control voltage amplitude, phase angle, and line flow, and to increase active power transfer. The static synchronous series compensator, or SSSC for short, consists of a synchronous voltage source on a transmission line. It supplies the appropriate voltage to the line for the phase angle, thereby changing the impedance of the line. In a PSAT simulation, both TCSC and SSSC increased static load and voltage stability limits, increasing the power transmission capacity of the line. Each of the mentioned FACS devices performs dynamic power factor correction via different methods and with varying degrees of effectiveness. By simulating and comparing these devices, individually and in combination, one should be able to determine the optimum reactive power through a given branch and the relationship between required reactive power and power factor correction. One of the studies I read, which can be found in reference 5, used a 2-bus pi network model consisting of a generator bus and a load bus to represent an equivalent multi-bus system for the rapid assessment of voltage stability among fluctuating loads. The authors determined optimal power flow, or OPF, with successive incremental increases in load at the weakest bus without a FACS device, at the weakest bus with an SVC, and at a critical line connected to the weakest bus with a TCSC. They found that the SVC provided voltage stability at higher loads than the TCSC did. However, the TCSC provided better stability over the range of operating loads. This model is more sensitive to system status changes than the 2-bus series equivalent model is. In addition, the ability of this model to quickly assess voltage stability makes it useful for monitoring power systems in operation. When photovoltaic systems are integrated into the electrical grid, FACS devices are needed to provide power factor correction at the point of common coupling, or PCC, the point at which the PV system connects to the electrical grid, to maintain voltage stability in the grid. One of the studies I read, which can be found in reference 2, modeled a system in PSCAD which tied a PV array into the grid. This system consisted of a PV source, a DC link capacitor, a DC to DC converter, a DC to DC controller with maximum power point tracking, or MPPT, a grid interface inverter with a filter, and a step-up transformer. The DC link capacitor generates the reactive power. The maximum power point is tracked by means of the incremental conductance algorithm because it is the point of maximum efficiency and output power in the PV system. In the study, several different load values were used to determine the ability of the PV to correct the power factor at the PCC. This design allowed the PV system to compensate for excessive reactive power at night and to supply reactive power during the day. The ability to tie renewable energy sources into the grid is becoming increasingly important as energy policy continues to put more emphasis on renewable energies. As a result, power factor correction at the PCC takes on greater relevance in maintaining grid stability, and this must be dynamic to compensate for widely variable loads. Here are the references I used for my paper introduction. I believe I have clickable links in my paper if you wish to access them. Thanks for watching, and I hope you enjoyed this video, and I look forward to your questions and comments.